people will be mad at me. Okay. Hello again. Now you can hear me. So you didn't lose much. Sorry, I forgot about the screencast watchers. Anyway, what I wrote is basically what I said. I didn't give out any secrets. So, all right, so that's that. And so I want to get a transfer function out of this, okay? So one idea would be to take the Laplace transform of both sides of this differential equation. Okay, Laplace transform of this and Laplace transform of that, they'll have to match, right? So can you tell me, of course, Laplace transforms are linear, so you can apply them piece by piece and add. Okay, so what would you say is the Laplace transform of the first term, the one that I just underlined, in terms of the Laplace transform of y of s? Well, maybe we should start with this. I know some of you know the answer, but this will be a0 y of s, correct? All right. This will be s times y of s. Remember the differentiation property? Differentiation property said if I take the derivative of a signal, the Laplace transform gets multiplied by s, right? So when you see s, think of differentiation. When you see 1 over s, think of integration. Okay, that's fundamental. And what would you say for this? S to the n y of s, right? Same thing for the right-hand side. I get bm s to the m x of s to b0 x of s, right? So I can factor out y. So I get a polynomial multiplying y. A1s plus A0 y of s equals bm s to the m to b1s plus b0 x of s, right? Looking at this expression and this y of s, h of s, x of s equation above, can you tell me what h of s is? Just look at the two shaded lines. What is h of s? Yeah, h of s is y by x, right? Y of s by x of s. Can you see the bottom of this? Yes, you can. Great. Equals bm s to the m b1s plus b0, right? Divided by an s to the n a1s plus a0. And there you go. That's how you find the transfer function, right? Very simple. I mean, you don't need to do this derivation, obviously, every time. You just observe the pattern here. You take the coefficients of the differential equation and make them coefficients of the polynomials. You have a denominator polynomial that comes from the right-hand side of the differential equation involving the input. And you have a denominator that comes from the left-hand side involving the output, right? So that's the transfer function, and it's very easy, therefore, to take a differential equation model represented as a transfer function. We did this, I didn't tell you then, of course, because we had not seen Laplace transforms yet. We did something very similar for finding the frequency response of differential equation models. So this is, of course, more general. You can do that first. This is easier to remember anyway, because there, instead of s, we were taking j omegas, right? It was j omega squared, cubed, etc. Now it's all s, just one complex variable. If you want to recover the frequency response from this, just substitute s equals j times omega, right? Okay, so simple then, right? Fairly easy. So if I want to recover the frequency response, I take h of s, substitute s equals j omega, and I get h of j omega. That's one of the reasons why we were writing the frequency responses in this fashion, h of j omega, because then you can immediately link it to the Laplace transform, okay? So frequency response. Okay. Now, last time we talked about poles and zeros of Laplace transforms. They were the roots of the denominator and the numerator of the Laplace transform. When we talk about poles and zeros of transfer functions or systems of, let's say, transfer functions, if I say the pole or zero of this system, I'm actually referring implicitly to the transfer function. They are the roots of the numerator and polynomial. So if I write h of s, which I just wrote earlier, let me go back and copy that. If I manage, I don't know which one is faster, writing again or doing this funny thing, but see, I think writing is faster. Anyway, you remember, so we start with bm, s to the m, go to b0, right? And in the denominator we have an, s to the n, and we go to a0. So this is the numerator here. I'm going to call it n. And this is the denominator. I'm going to call it d. So the poles of the system, poles of the LTI system, are basically the roots of the denominator polynomial of the transfer function. So the set of all s such that d of s equal to 0. Since d of s is a polynomial of nth degree, how many poles am I going to get? N poles. No, n poles? Yes. Yeah, n poles. And then zeros are the roots of the numerator, s such that the numerator becomes 0. The numerator being an mth order polynomial, we'll get m zeros in this model. All right? We'll talk a lot more about what to make of poles and zeros, how do we interpret them, what does it mean to have a pole here, zero there, right? What kind of conclusions we can draw from pole zero locations. We'll discuss that today, all right? But let's think about an example. So the circuits are always nice for examples of differential equations because at least the majority of you took 16. You've seen a lot of, or some circuits. And so you have some intuition about how they behave. So that's why I tend to use circuit examples. But I do not expect to know everyone to know much about circuits anyway. So x of t is going to be the voltage that I'm applying to an RLC circuit. There is a resistor R. There is an inductor L. And then there's a capacitor C. And the current that flows in this direction, I, I'm going to call it y of t. That's the output that I'm considering. So, you know, it's a physical system. You can define your input and output as you wish. In this case, I'm treating the voltage as an input and the current that flows through the circuit in this shown direction as the output, right? So what is the transfer function of this system? What is the right approach for this? First, I can write a differential equation model for this, right? And then use the tricks we learned to turn it into a transfer function. So, any ideas about how to write a differential equation? Put a dot? What do you mean put a... Oh, I see. Okay. All right, got it. So, all right, so let's maybe think about the voltage across all of these elements, right? From Ohm's law, this is R times I. I'm going to drop I and write Y because that's what I'm doing here. I define it as my output, right? And then how much, what is the voltage across the inductor? L dy dt, right? That's one of the laws we discussed. Okay, so then the voltage across the capacitor, it has to be x take away ry and L dy dt, correct? So the voltage here is x of t minus r y of t minus L dy of t dt. All right? Do you guys agree with this? Okay. So now to turn this into a differential equation, I have to also use the rule we have about a capacitor, right? Capacitance C times the derivative of the voltage equals the current. So if I write C times d by dt of this voltage here, which is x of t minus ry of t minus L dy dt, that is going to be the current, which is y. Okay? So that really is our differential equation model. We just have to simplify it a little bit. So for one thing, we can move all the y terms to the right-hand side. So we'll get, what do I get? Yeah, so this will give us the second derivative, right? Because we're taking the derivative again. So I'll have L times the second derivative of y, also multiplied by c. So I'm going to have LC d square y dt square. And then RC dy dt plus y. So I moved all the y containing terms, this and that, to the right-hand side. Paired it with the other y term. The term that remains on the left is c times dx dt. All right? So what is the transfer function? So, you can try to remember this formula we have, that tells you how to map the differential equation coefficients to the polynomial coefficients, right? Or simpler yet, just so you don't have to memorize anything, just look at this expression, and everywhere you see an x, d by dt, think of it as s, right? So the left-hand side, so basically I'm suggesting doing our derivation all over again, which is not a big derivation anyway. So the left-hand side looks like cs x of s, right? And the right-hand side looks like LCS squared plus RCS plus 1 times y. Right? So therefore, am I doing this correctly? I think I am. All right, so therefore, the transfer function is, can somebody say, just using this, CS goes in the numerator. Remember, all the terms containing the inputs, they go in the numerator. And the denominator will have LCS squared plus RCS plus 1. So that's my transfer function. That's the final answer. Okay? So there you go. You start out with a circuit. Now you look at it as a transfer function. If you want to see the frequency response of the circuit, just substitute S equals j omega, and there you have it. Okay? Sometimes people say, what is the order of this system? Order means, what is the largest derivative of the output that's involved? So in this case, it's 2, right? So that really translates to the order of the denominator polynomial. So in the denominator, we have s squared, so we call this a second order system. Okay? If you had seen an s cube in there, you would have called it a third order system. All right. So can you tell me about then the poles and zeros of this system? So there is 1, 0, right? At s equal to 0. There are how many poles? 2 poles. And they are, you can just use the usual formula for that. I might even need a little help myself. Negative RC plus minus R squared C squared minus 4LC. Is that it? Yeah. And now you take the square root of the whole thing. Divide by 2 times LC because that's the coefficient of this. S squared term, right? So are these poles going to be real, imaginary? How do we know? Depends on what's in the square root, right? If that's a positive term, you're going to end up with 2 real poles. If you have a negative number in there, then you're going to end up with 2 complex conjugate poles, because it's plus minus. It's going to be plus minus j times something, right? Make sense? All right. We'll talk more about poles and zeros. Just as a short break, I want to give you a little history of this person who invented those ideas without knowing anything about Laplace transforms. Laplace transforms came later. Other people wanted to make it look more mathematical, and they dug out this some ideas by Laplace from a century ago, basically. So the guy who invented these ideas was Oliver Heaviside. He was an eccentric person, okay, very eccentric. So I think he was working on some telegraph lines which were being laid out at the time across the Atlantic, and people didn't completely understand the transients and things of that sort. So these differential equation models, including inductance, capacitance, etc., were critical. And he developed ways of dealing with those. But then he got bored of the work he had to do with the office he was working in, so he just quit and moved in with his brother, lived in a room, wrote his papers, didn't interact with anybody else. He's done a lot of things that we use in EE courses. For one thing, he introduced these ideas of transfer functions, essentially. He used these Laplace-like things without calling it Laplace. He used the variable s as a differentiation operator, right? He says when you see dy dt or the derivative of something, think of it as multiplication with s. And that's how he was able to turn differential equations into, transfer functions, polynomial by polynomial. And he developed a method for, reasoning about their behavior using the poles and zeros. So those are all his ideas. So he called this operational calculus. Instead of dealing with a differential equation, you deal with polynomials. Calculus coming from representing derivative with s, or second derivative with s squared, and so on. He named some of the circuit elements. He called, for example, the terms impedance, inductance, were coined by him. He also looked at this very complex paper of Maxwell that nobody fully understood, and distilled it into the 4 equations that we talk about today. If you've taken a course on electromagnetics, you've seen 4 vector equations that are called the Maxwell equations. They weren't like that. Maxwell didn't distill them to those 4 equations. So this guy did. All right, so one of the great ideas here is, when you look at a circuit like the one we were discussing, he was thinking all of these elements, L, C, instead of using these differentiation rules like L times dy dt is the current, that kind of thing, he started thinking of these as resistances, but including S. Like everything was like an Ohm's law. So in his view, you have an input X. Can you see this? Yeah, input X. All right. And then a resistor R, an inductor L, which he'll think of it just like in Ohm's law. Instead of L, he'll write L times S. Okay? And then instead of C, because that's basically integrating, he'll put C over S. Okay? So then you'll manipulate, so the current is Y, right? Just like the way you would use Ohm's law. If these were all resistances, what would you do? You would take the voltage X divided by the sum of the resistances, right? And that would give you the current. So he does the same thing. So he says, okay, Y is voltage by resistance plus Ls, which is inductance, which is treating as if it was some kind of Ohm's law, and C over S, right? And if you simplify this, you can multiply the denominator and numerator by S. So you'll get S by L. What am I doing here? What did I do? 1 over SC. You're right. Yes, that's why this was going in the wrong direction. Okay. Thank you. So 1 over SC. Okay, then let's multiply everything by CS, okay? So we will get LCS squared RCS plus 1 times X of S. And here comes the same transfer function. Right? Isn't that cool? It's just using Ohm's law, pretending these are like resistances, except with that differentiation operator S treated as part of that. Okay? So that's the guy. He had lots of simplifying ideas. A lot of things we teach in at least upper division courses have something to do with him one way or another. Sometimes in some books, for example, you can see the unit step function called the Heaviside function, because that's one of his ideas also. All right, so much for Heaviside. I can say safely that for our purposes, Heaviside is a more important person than Laplace. Okay? He didn't worry about regions of convergence, things like that. He just wrote these polynomial equations and manipulated differential equations, predicted their solutions from the polynomial's roots and stuff like that, right? Later, people felt that this needs to be mathematically more sophisticated, and they linked it to Laplace transforms, etc. But really, for the purposes of this course, and perhaps 128 if you take it, all you really need is this operational calculus of Heaviside. Okay? I taught you about Laplace transforms because if you interview for a job and if they ask you what's the Laplace transform of this, and you say you mean the Heaviside, and I don't want you to have that experience with your future employer. But really, that's what we need. All right. So anyhow, so let's talk about what poles mean. I mean, the fact that I have a pole somewhere, what does that? What should I expect from that system, right? So remember our trick last time. We would take an h of s, a polynomial by polynomial, rational, right? And then we do a partial fraction expansion. The whole idea in partial fraction expansion is to break up h into a sum of first order terms if possible. And if that's not possible, if you have repeated poles, then you may need second and third order powers. PFE. All right, so the idea is let's assume there are no repeated poles. Assume no repeated poles. That means I don't need to go to higher powers. I can represent the whole thing as some number A1 by S minus some number alpha 1. That can be complex, that's fine. A2 by S minus alpha 2. And if I have n poles, the denominator is an nth order polynomial. So we have n roots, and so you're going to go all the way to S minus alpha n. There will be n poles. Again, we're assuming none of them are the same. Alpha 1, alpha 2 to alpha n. They're all distinct. All right? So I can do this. I can match coefficients and figure out what the A1 to AN are. Right? So you have your partial fraction expansion. So then what do we make of this? Well, looking at this, you can actually tell me the inverse Laplace transform very easily, right? Which is, of course, this being the transfer function, inverse Laplace transform is the impulse response. So what's the impulse response? I'm going to assume causality because circuits and other physical systems run forwards in time. Okay, causality. Therefore, you're going to give me a right-sided solution. Remember from last time, the inverse Laplace transform can have multiple answers unless you specify the ROC. Going forward, more than specify the ROC, we'll stick to causality or right-sidedness, and you'll get one answer. So the first term is alpha 1t, a2 e to the alpha 2t, an alpha n t. All right? Ooh, what am I doing? E to the alpha n t. Now, so that tells you why we care about poles. These are, if I excite the system, if I pulse it, somehow apply a voltage and make it disappear, right? So I just give an excitation to the system. So it will jump because of the impulse. And what are the subsequent dynamics, right? What happens next, right? H of t is basically that, right? How do you respond to an impulse? And this tells you all about it, right? If I excite my circuit, for example, it has two poles. How it reacts to it will depend on the poles. Does that make sense? Yes? Because that was one of the last things we did last time. If you have repeated poles, I will have to include the second power of that pole, s minus alpha squared. For now, I don't want to get into that, but it's very easy to extend. I will do it in a second, okay? So is that clear? Yes? So poles matter because they tell us about the nature of the system's response to an excitation, right? Even if it's not impulse, even if I apply a step, that will be the convolution of the step with the impulse. So whatever exponential terms you're seeing here, you will continue seeing them at the output in addition to the steps effect, right? So these are fundamental things. This is the nature of how the system reacts to things, right? Does it react like crazy, jumping up and down, or does it react calmly? They all depend on the poles, all right? So a system, let's say a system with poles that are here and here. Negative real parts, but they are complex. So how does this system react to an impulse or anything else? Is it, what kind of reaction is that? So it will be something like, there will be oscillations, but it will be decaying, right? If you have, that's not the best drawing, but I hope you're understanding. If I have a single pole, what is the response? Just an exponential delay, right? So, yeah, that's why we get a lot of intuition. For example, whether or not the poles are complex, that will determine whether you'll see oscillations in your system response, right? So, very critical information, right? All right, so there was this figure in lecture 3, and if you took 16b from me, or if you saw my notes somehow, that was also there. I told you I will bore you to death with that picture. You'll see it a million times, so I'm going to show it to you again. Here is my favorite picture. Where is it? There it is. Mapping poles. This is basically showing you several locations of a complex number and e to the st when s is one of those numbers, right? So this tells you what to expect, right? If you have poles on the right half plane, that's not good. Why is it not good? You're exploding. You're just unstable. If you have things to the left half plane, you may be excitable, you may just oscillate, but you'll be decaying. Poles that are really far in the left half plane, they die down very quickly, right? Even if they oscillate. Poles that are on the imaginary axis, they don't die away. They just continue oscillating or stay constant if you're exactly at s equal to 0, right? Poles that are close to the imaginary axis, although they're on the left half plane, they will keep ringing, they will perhaps die out, but it will take a long time, all right? So, poles matter. In fact, when we design controllers, you'll see some examples of this. Most of it is about putting the poles in the desired locations, right? How do you want your system to react to, say, a step change, right? Do you want it to oscillate, or do you want to go smoothly to the new set point? That's all determined by the poles are, by where the poles are, okay? So I took a flight. This is one of my favorite stories. I took a flight, and then it was the end of summer a few years ago. So we were ascending, and then we started going down, which is never good. You don't want to. If you're in that phase where you're ascending, you don't want to be. There's never a good explanation of going down, okay? But then we started going up and down, and some people were freaking out, but I thought, well, it's just the controller not tuned properly. So, the poles are imaginary, obviously, and too close to the imaginary axis. So that was my explanation. So I was pretty calm. So taking signals and systems helps you in many ways. And I actually asked the pilot at the end. He agreed. He said during the summer they overwork the fleet because a lot of people are traveling, and they fall back on maintenance. So things get out of tune. Nobody has time to fix them. So things like that happen at the end of the summer, he told me. Anyway, we still have to travel anyway at the end of summer. All right, so what if we have repeated poles? That doesn't really add much. So if say alpha 1 is, I just called it alpha 1. Let's say the first one is repeated. Is a repeated pole with multiplicity, meaning that it's repeated that many times. Multiplicity m, okay? So m1 means it's not repeated, m2 it means you have two poles at the same point, right? Then, when you're doing your partial fraction expansion, let's see if you got that point last time. It's not going to be enough to put just a1 by s minus alpha 1 to the power m. You're going to have to go all the way down to, s minus alpha 1, m minus 1, and finally a single s minus alpha 1, right? So for that reason, we're going to index these with a second number, m minus 1, and this will be a11, right? So the partial fraction expansion has to include all of these terms, right? Does that make sense? We saw this in an example last time. We had a square term, the pole was repeated with multiplicity 2. We didn't just include s minus alpha squared, we also had s minus alpha. Just for fun, you can try this on your own. Try to not add these terms, the other terms, okay? And try to match the things when you're doing partial fraction expansion. Most likely, you're going to end up with equations that don't have a solution, mainly because you didn't include the other terms, right? Okay, so, but then what kind of time functions in the response do these result in? This I know, it's going to be a11 e to the lambda 1t, right? What is that going to result in? Yeah, the moment it's repeated the second time, you get t times that exponent, right? There may be some coefficients, so I'm not sure. You'd have to look at the exact expressions. I think there's a factorial of something somewhere. That's in the notes last time, by the way. But the important point is that you're going to end up with t to the m minus 1, which simply means it's not there when the multiplicity is just 1. Oh, wait, I'm talking about this, sorry. Okay. So the last one, right? That will give you t to the m minus 1 e to the alpha 1 t, right? So exponential term multiplied with a polynomial term. And this one will give you t to the m minus 2. I'm basically taking the power and subtracting 1 from it, because when the power is 1, we have 0, t to the 0, which is 1, right? E to the alpha 1t, etc., right? So you get additional powers. But they still behave very much the same way as exponents. We discussed that last time. Exponential functions always beat out polynomials. If exponential wants to decay, polynomial wants to explode, exponential wins. It decays after some resistance. So you would have some growth and then decay. All right. So that's that. So going back to the circuit example, we found the poles to be at, where were they? I lost my poles. Anybody seen my poles? So negative RC plus minus R square C square 4LC square root by 2LC, right? So when will this give us oscillations in its transient response? Oscillations, this is one of the takeaways from this course. You've got to be able to link oscillations to complex poles, okay? Oscillations, complex poles. That's what that figure is doing. That's why I keep showing that to you. Complex poles, if this number here is negative, because that will introduce plus minus j times something. So that negative means, I guess I can cancel C r squared C less than 4L, right? So clearly what will contribute to this is a big inductance, right? Or a small, relatively small resistance and capacitance, right? So inductance is basically causing these oscillations because the energy is flowing back and forth between the capacitor and the inductor. And it's being dissipated along the way by the resistor. So the reason that we have a real part here, negative real part, right? So the poles are here, right? Even when this is the case, we're going to have a negative real part. So it's going to look like this. Correct? And that's because of this negative RC term. If I omit R, if there's no resistance in the circuit, then what happens? Where do the poles go? They fall on the j omega axis, right? So that means there's no dissipation. There's no dissipation is caused by the resistance, so they will keep oscillating. They'll never die down. And that's basically L and C together will give you an oscillator. They'll push the energy back and forth between them. But if there's resistance, it gets dissipated. That's why we have an envelope that the oscillations follow. All right, so that's what the poles tell us. What do we learn from the zeros? So this is actually even easier to explain. We don't have to do anything about Laplace transforms. So let's say we call the poles alpha, right? So suppose, so we're going to call the zeros beta, okay? Suppose S equals beta is a zero of h of s. So then, let's say I'm applying as my input e to the beta t to my system. Remember, lecture 2 or 3, one of those lectures, without doing anything else, just using convolution, we said any exponential signal driving an LTI system will show up at the output multiplied by the transfer function, h of s, right? Even when we didn't know Laplace transforms. So it's going to be h of s, but s in this case is beta, right? H of beta e to the beta t, right? So that's something we discussed way back. So e to the st gave us h of s times e to the st, right? Now I'm saying let's substitute the actual value of beta, which is the 0, right? So what happens to h at the 0 when beta is the 0 of h? It becomes 0. So what is the output? 0. So that's kind of funny, right? So this is a input signal you're applying, and nothing happens. The system just doesn't see it, doesn't react to it. Okay? So therefore, the meaning of a 0 is a exponent, which if it's present in the input, it will be completely eliminated from the output. Does that make sense? For example, if I go back to the circuit, did it have any zeros? It has a 0 at 0, right? So what are the inputs that the output will not see? Constants, right? Because e to the beta t, in this case beta is 0, so we'll talk about e to the 0, which is constant, right? So that basically means, fine, you can have a constant input, the output will be 0, right? Which is consistent with the structure of the circuit, right? Because if I have a constant voltage, the steady state current will still be 0, right? The voltage in the capacitor will balance that out after some transients, and they'll settle, no current will flow. So that's basically the meaning. So these are the types of zeros tell us about the types of inputs that will be blocked by the system. All right. So, okay. Let's take a short break because the next part is not breakable into 2-3 minutes. And in the meantime, there's candy here for Halloween. right, Vlad is here. Let's start. All right, so now we have a transfer function. What else can we do with it? We can look at its poles, predict what kind of response we'll get to impulses. We can look at the zeros and predict what kind of inputs will get blocked. So we can also use this intuition to go further and say this system is stable or not stable, right? How do we do that? First, let's recall two things. In the earlier lectures, we talked about causality and stability, both determined from the impulse response. Let's see how well you remember that part. So how can I tell if my system is causal if all I have is h of t? H should be 0 before time equal when t, for all t less than 0, right? Otherwise, that means you knew the impulse was coming in the future. How would you do that if you're causal, right? Stability. Absolute integrability. Yep. It needs to be bounded. All right. So those are the two things you already know. Now we just basically have to translate these to the transfer function. So I'll give you the result right away. The most important part in this discussion is stability. So this is the result, and we'll discuss where this comes from. We'll make causality an assumption. We're interested in systems that are causal to start with. Okay, a causal LTI system will also assume that the transfer function is rational, meaning that it's a polynomial by polynomial, because that's the type of transfer functions we've been dealing with when we take the inverse Laplace transforms and so on, using partial fraction expansion. So with rational transfer function, h of s. So far it's vanilla. I'm just writing the assumptions, okay? Now comes the important part, is stable if and only if. That means this is both a necessary and a sufficient condition. If and only if all poles of h of s have strictly negative real parts. Okay? If there's one message to take away from today, if you had memory enough only for one sentence, this is the sentence you should leave with. Okay? Stability for a causal LTI system means poles are in the left half plane. Strictly negative real part means they lie to the left of the imaginary axis, right? So if this is the imaginary axis, this is the real line, you will be stable if all of the poles are to the left of the imaginary axis. If you have anything to the right, doesn't matter where all the others were, you're unstable. This is not a stable system. All right? So this condition that everything should be on the left half plane should not be too surprising because of my famous picture. Right? This is what's in the system's response, right? If you have anything on the right half plane, it's ready to explode. That's a signal, sign for instability. But let's discuss how we actually reach this conclusion more concretely. So there are really two observations that lead to this conclusion. First, I assume causality, right? So what does causality mean? Causality means H is right-sided. Okay? So two observations used in the proof. Really, two steps basically, not more than observation. Two observations used in the proof are, first, if the system is causal, that means H is right-sided. So what kind of region of convergence do we associate with right-sided signals? For example, 1 over S plus A. Remember the example from last time? 1 over S plus A goes with e to the negative at u of t, right? What is the ROC? Greater than minus A. So we saw last time in examples that it's always to the right of the pole. The pole will be at most on the boundary. It can't be inside the ROC because it's infinity at the pole, right? So causality means basically ROC is to the, or what's the better word? ROC is the half plane, just like in this picture. Half plane demarcated, is that a word? Demarcated by the rightmost pole. Okay? So I'm writing this without detailed proof. Take it as a fact, because I decided not to do a big deal of regions of convergence, but it turns out that under the rationality assumption I made, we're going to have poles, and then the rightmost pole, the ROC, since h of t is right-sided, will exclude all the poles, and the rightmost pole will be on the boundary. Right? Maybe blue is a better color. Okay? So that's one observation about causality and ROC. So given that we assume causality, then we'll talk about ROCs that are to the right of the rightmost pole. The second observation is about stability. Stability is absolute integrability of H, right? Stability is the same as absolute integrability of H. Not H of t times e to the negative sigma t. H of t. All right? So remember, absolute integrability of x of t e to the negative sigma t determined whether or not the line where the real part is negative sigma is in the ROC or not, right? Because if that's absolutely integrable, when multiplied by e to the negative j omega t, this integral will converge, right? So since we know that stability means H itself without any sigma is absolutely integrable, then that means the imaginary axis, where sigma is equal to 0, is inside the ROC. Does that make sense? Yes? H is absolutely integrable, so it has a Fourier transform. Maybe that's a simpler way to put it, right? Absolutely integrable signals have well-defined Fourier transforms, right? So if the Fourier transform exists, the ROC of the Laplace transform must include the imaginary axis. Okay? So ROC includes imaginary axis. All right? So if I put these two observations together, I reach the conclusion that I said for stability of a causal system. The first one, by causality, the region of convergence lies to the right of the rightmost pole. That's my ROC from 1. Okay? And 2 says the ROC includes the imaginary axis. Okay, so the imaginary axis has to be within the shaded region. Okay? So we put these two things together, and what do you see? ROC must be to the right of the rightmost pole, and it must include the imaginary axis. Therefore, all of the poles must be to the left of the imaginary axis, right? That's it. So it's a combination of two observations. Okay? So this picture is the proof. all poles must have negative real parts. Okay? So we have a simple stability test. I look at the poles. Are they all in the left half plane? If they are, stable. If not, not stable. So let's talk about some examples. Start simple. H of s 1 over s plus 1. Since I know this is the transfer function of a causal system, that's the assumption of the theorem, right? Then h of t is a right-sided signal, which is e to the negative t u of t. What is another signal that would have given you the same transfer function? That's a pop quiz for the beginning of last lecture. Put a negative sign and flip u. So it's a left-sided signal, right? So they both give you the same transfer function. But this is disqualified because it fails the causality condition. By the causality, the only viable h of t is this one, right? And is this absolutely integrable? Yes, because it's exponentially decaying. Exponentially decaying things are integrable. Done, okay? So I'm basically, with these observations, I'm going through the proof again. Really, all you have to do is look at the pole. There's only one pole at -1. That's negative. Done. Stable. Anything I wrote to the right is sort of reminding you of what was in the proof, all right, of this statement. Let's look at another example. Example, h of s minus 1 by s plus 1, s minus 2. All right, so what can you say about the stability of this? Poles at -1 and +2. -1, +2. Stable? No. Who's the culprit? This one. This one. Right half plane is not allowed. Again, what went to this is, if you look at possible h of t's that give you this h of s, and ask which ones are the causal ones. So, as a quick exercise, I guess, I could just do a partial fraction expansion, which I'm not going to do, but I'll tell you the answer. I can say this is 2/3 of s plus 1 plus 1/3 s minus 2. If you don't believe me, just simplify this, make sure it matches the left-hand side. So now what is the causal h of t that would give rise to this? It'll be 2/3 e to the negative t and plus 1/3 e to the 2t u of t. Okay? Is that absolutely integrable? Absolutely not. Because of this guy who's exploding, right? Shortly, as you start at time equal to 0, this will be very small, but e to the 2t will keep growing, and that will dominate the whole thing. You can't integrate that. That's not even bounded. Okay? So not absolutely integrable. Now, if you really wanted, you could find an h of t that gives me this transfer function that's also absolutely integrable. Any ideas how I might find one? You see, this part is not the offending term, so I can keep that, right? So I could have h of t 2/3 e to negative t u of t. That is fine. That integrates from 0 to infinity, right? But what is another term? What would be another term that gives me this transfer function, but perhaps is integrable? What is the other candidate? -1/3 e to the 2t u of negative t. Now that's an interesting signal. For although it's e to the 2t, this is only valid for negative times. So e to the 2t looks like this. It's exploding for positive t, but then we kill it after time equal to 0. So it's like this, right? And then the right-hand side, you would have this term for positive t. So both sides are exponentially going to 0. So this candidate is actually absolutely integrable, because from both sides it's going exponentially to 0. But it's not causal, and therefore this is not an option for us, right? That's what's in the proof, all right? So we assume causality because all these other options go away. They are not consistent, so absolute integrability is the one, and combined with causality is what forces the poles to be on the left-hand side for stability. One last example, which is actually quite important, which will answer the following question. What if I have poles on the imaginary axis? Look at the way we wrote the statement. Is that allowed? Can I have a pole on the imaginary axis? Okay, so clearly somebody thinks, and this is also if and only if. There's no negotiation here. If and only if. So if I have something on the imaginary axis, I am unstable. So how is that so? Why do you think that is the case? Yeah, it may not be clear by looking at my famous picture why that's so, right? Because you have poles on the imaginary axis here, right? And the impulse response contains these things that keep ringing, but they don't go to 0, right? But they don't explode either. So why should I consider this to be unstable? Bounded input, bounded output, right? So I don't see anything unbounded, any unbounded growth here. But remember, this picture is when the input is the impulse. What if it's something else? The question is, can I drive this with a bounded input and see the output growing unbounded? Well, you'll have to take a convolution, right, with the input. So can you imagine one of these things, you know, the ones that ring but don't decay, being convoluted with something else and giving you something that explodes? Yeah, what's an example? U of t, yeah, even look at the one at s equal to 0. U of t, convolution with U of t, it grows, right? So that's the reason. So that's what this example illustrates. So it's actually, the example is h of s equals 1 over s. And what that system does, give me a differential equation that does this. Remember, that simply means y of s by x of s is 1 over s. Therefore, y of s is 1 over s times x of s, or x is s times y. Wait, what am I doing? No. I'm sorry. Yeah, that's right. Okay, s times y is x. S times y is x, right? But what is this in time domain? d by dt y of t equals x of t. All right, so basically the output is integrating the input, right? So if I give it a constant input, you integrate the constant and grow unbounded. That's basically it, right? So if x of t is step, u of t, then x of s, what is the Laplace transform of the step? One over s. So therefore y of s is 1 over s squared. Okay, 1 over s is the Laplace transform of the unit step, right? So we're talking about Laplace of unit step times Laplace of unit step, which basically means unit step convolution with unit step, right? So if you go back to the time domain, from the derivative properties we derived last time, this is going to give you t times u of t. that you could also have concluded just by doing the convolution. This is u of t. Input is also u of t, so you flip it and drag it. And then the area is the output. So as this keeps growing, the area grows linearly. That's why you get t times u of t, right? Isn't it nice to be bilingual, frequency domain, time domain? You can do these things as you wish, whichever domain you're in. Similarly, and remember, an important statement about the definition of stability. Stability means any bounded input will keep the output bounded. All right? Unstable means not stable, meaning that there is one input out there that's bounded, and yet the output is unbounded. All right? So if you want to show instability, you're just looking for one input. There may be other bounded inputs that will somehow keep the output bounded. That doesn't matter. If there's one bounded that keeps it unbounded, you're unstable. And that's exactly the case here, right? So if my transfer function is 1 over s, if I'm integrating, there are other things, other inputs that are bounded that will keep the output bounded, right? What is a bounded input whose integral is still bounded? I mean, even things like sine and cosine, right? They are not going to hit you at the right frequency, right? If you're just integrating, you integrate sine, you get a cosine or something like that, right? So you remain bounded. So the essence of this argument here is that, again, going to my picture, to create instability, wait, that's not my picture. Yeah, here. To create instability, you have to hit this system with an input that matches the pole on the imaginary axis. If the pole is at 0, you have to hit it with a constant input. Then you take the convolution of a constant input with a constant input, and it blows up, right? If you have a pole with an imaginary real part, that means you have oscillations. If you apply an input that has the same oscillatory frequency, then the convolution of the two will grow unbounded. Okay? So one is enough. I can apply a sinusoidal thing to an integrator, doesn't blow up, that doesn't mean it's stable. There's another input, which is a constant, that will drive it unbounded. All right, so I think this will make for good homework problems. I'm thinking as I'm teaching. All right, one example to finish this discussion with. Analog filters. In fact, a very special class of analog filters called Butterworth filters. Even though everything today is digital, we still need analog filters. Why? Give me one reason. Yeah. If you're doing, remember that block diagram, you first do C to D, and then do your digital processing, and then you do D to C, right? Even though you could be implementing a digital filter, well, first of all, you have to make sure before sampling that you're going to not have aliasing, right? Before sampling, you have to make sure to cut off the high frequencies of the signal, or at least reduce them to a negligible level. All right? Well, how do I do that? If I have to first sample to filter, that defeats the purpose, right? That's the circular argument. So first I have to do an analog filter, take my continuous signal, make sure its spectrum is now bounded, it's a finite bandwidth, and then sample fast enough so that there is no aliasing. And then you can do fancier digital filters. But first you need a quick analog filter to cut off the high frequencies, right? So they remain relevant in some niche corners, analog filters. And so Butterworth filters are a very special class. They are nice and smooth. So the frequency response of a Butterworth filter looks like, so first of all, an important parameter for a filter is the cutoff frequency, right? And usually that cutoff frequency is defined to be, if you are designing a low pass, it's going to be 1 at the 0 frequency, right? And cutoff frequency is defined to be 1 over square root of 2, right? So until you reach like 70-something% of the DC value 1, you consider it a pass. Once you fall below, you start considering it eliminated, right? So basically the type of filter we want here is like something that decays like this, right? So there are several filter design methods out there for analog systems. They include Chebyshev, this and that, there are all kinds of names. But usually, they, either in the pass band, in the low frequency region, or in the stop band, in the high frequency region, they'll have ripples, okay, those designs. Butterworth is good because it's smooth all over. It's monotonically decreasing. You don't get these funny ripples, okay? So that's the idea of the Butterworth filter. And of course, the order of the filter, meaning what is the order of the polynomial in the denominator you're willing to have, determines how sharp of a transition you can have. So this might be, the one I showed you might be the picture of a low order Butterworth filter. A higher order one would be better in the sense that it will be going sharper to zero, declining more sharply around the cutoff frequency. Does that make sense? So this has sharper transition. To get a sharper transition, I'll have to have a higher order filter. Okay? So what makes Butterworth so smooth? Well, Butterworth filter is one whose frequency response is given by this. At least the square of that is 1 over 1 plus omega by omega c raised to power 2n. Okay? So that is the Butterworth frequency response. And if you plot that for a fixed n, you'll get figures like the one I show you at the top. To get a sharper transition, what kind of n do you think I need? Smaller, larger? Larger. And if n is 1, this is like 1 over 1 plus omega squared. That's pretty, gently decaying, right? Large n in this formula will make the transition a lot sharper while still making the response monotone decreasing. Okay, so the question is, precisely, given that this is the frequency response we are dreaming of, that's what we want to achieve, and that we're going to build a system that is real valued, with real elements, what is the transfer function that will give us this frequency response? So, and also we want causality, of course, from our filter. So what is the transfer function, I'm going to abbreviate it as TF, of a causal and real, or causal LTI system, and of course you want stability too. I'm saying my conditions one by one, but you want causality and stability. You're going to implement this. You can't burn your circuit. You have to be stable. You can't predict the future. You have to be causal. So what is the transfer function of a causal and stable LTI system? Also, this is going to consist of real circuit elements with real valued h of t. Okay? So this is the problem. And we're going to solve this together. All right. So, obviously, we have to work on this equation, right? This is our starting point, and we'll somehow try to map it to a transfer function. So, what is the norm? When I say A, if A is a complex number, right? And if I say A absolute value squared, what is this in terms of A and its conjugate? The product of A and A star, correct? For a complex A. right? So since h of j omega is a complex number, I can write h of j omega square as h of j omega times h of j omega star. Agree? If you agree to what I wrote about A, that's the consequence of that. Now, knowing that h of t is real valued, what can you say about h of j omega star? This must be h of negative j omega, the complex, what was it called? The conjugate symmetry property, right? So we have, so that follows from h being real valued, right? So we have h of j omega times h of negative j omega, and I know what that should be equal to. It should be 1 over 1 plus omega by omega c power 2n. Okay? Now, I'm going to ask you to look at this and say something about, try to connect it to an h of s instead. And to make your life easier, what's the connection between h of s and h of j omega? They're the same. Substitute s equals j omega, the other comes out, right? So to make your life a little easier, I'm going to put a j here. So it looks like not just omega, but j omega, which we can map to s, right? And to account for that, I'm going to put a j here as well, right? So from this expression then, can you tell me what h of s times h of negative s should be? Basically what you're doing is when you see a j omega, call it s, right? That's how we go between frequency responses to transfer functions. So what is the right-hand side then? We're going to take this j omega, call it s. Okay, 1 plus s by j omega c power 2n. Okay? Are we getting close? I asked you for h of s. I didn't ask you for h of s times h of negative s. Right? So we need to look at this and somehow figure out what is h of s. All right, so let me copy this. Paste. All right. So let's work on this. So if I look at the poles of the right-hand side here, poles of this are poles of h of s union poles of h of minus s, right? Okay, so that means, if I look at the poles of the right-hand side, there lies the poles of h of s combined with poles of h of negative s. And of course, these poles are mirror images of each other relative to the imaginary axis, right? Because h of s, h of negative s, right? You flip the sign, you're going to get the other pole. So let's find the roots of this polynomial then. So poles of this are roots of s over j omega c to power 2n equals negative 1. So what are the solutions of this, right? So a complex number raised to power something gives you negative 1. What can you conclude about the roots? Roots of unity. The trick in dealing with roots of unity is to say negative 1 is really e to the j pi, right? Also, there's flexibility. I could also call it e to the j pi times k times 2 pi for any integer k. Does that make sense? Because then you rotate it by another 2 pi, you're again at negative 1, right? So how many roots am I looking for? 2n. So then what I have to do is go from perhaps 0 to 2n minus 1. And then divide all powers by 2n. That means s over j omega c equals e to the j pi plus k 2 pi by 2n. And those are the poles of h of s times h of negative s. 2n minus 1. Oh, and then there's this term. Let's not forget that. So s is going to be omega c, which is just a scaling factor. That's the cutoff frequency, right? Times j times this. But j itself can be written as e to the j something. What is j in terms of, where does j lie in the complex plane? So the angle is pi over 2, right? So e to the j pi over 2, so that's j, times this. Pi over 2n plus, j, what am I doing now? K pi n, right? No, pi over n. Okay? All right, they can, of course, be combined. So, all right. So, okay, let's do an example. Let's take n to be, say, 3. Let's say n is equal to 3, right? That means we are looking for k 0, 1, 2, to 6, to 5. So we have 6 poles altogether, right? So what are they? For k equal to 0, what do you see? Take n equal to 6 again. I'm going to make a picture on the left. First of all, where do these poles lie? On a circle, right? What's the radius of the circle? Omega c. So this picture is a picture of the complex plane. That is supposedly, allegedly the unit circle. Okay. Now it's better. Okay. So k equal to 0. Where is the pole on the circle? Pi over 2 plus 60? No, 2n is, what is 2n? 6. 30. Okay. So we start at 90, add another 30, so it's going to be here. So this is 30 degrees, right? So this is k equal to 0. Okay, k equal to 1. That's easy because at each next k, we're going to increment by how many degrees? By 60, yes. So another 60 will put me here. That's k equal to 1. Another 60 will bring me here with the 30 degrees again. That's k equal to 2. 60 from here will be this. K is 3. K4 is here. And K5 is here. So the 6 poles you're looking at here are the poles of h of s combined with the poles of h of negative s. Therefore, to each s, to each pole, negative of that pole should also be a pole. Do you see that? Good. Okay, so this is the way it should look. Not all of these 6 poles, of course, belong to h of s. Only 3 of them do. And it's up to us to choose which 3. Subject to the constraint that I'm going to actually have to implement this, and I want it to be stable. So which 3 should belong to h of s? The left ones, right? That's our stability condition. So these 3 should be the poles of h of s if h is supposed to be the transfer function of a stable system. Okay? So that's the idea. That's the pole structure of a Butterworth filter that is of degree 3. If you have higher degrees, there's a formula. You still have poles on the half circle. Stability restricts us to the left half plane. So it's not the whole circle that's relevant, only the half circle to the left. Okay? So when you look at the poles of Butterworth filters, they're always on a half circle in the left half plane. And they start with pi over 2n degrees from the imaginary axis, and they go by pi over n. So you can increase the order as much as you wish. For example, if you are doing, I don't know, n equal to 5, a higher order filter, Butterworth filter, the poles would be on this half circle starting at pi over 10, right? Which is 36. Okay? And now you go by 70 to, what am I doing? No, that's not right. Pi over 2n. Pi is what? 180. 18, that's right, 18. You start with 18, go another 36. Another 36 will put you here. Another 36, and another 36. Those are the poles of a Butterworth filter that is of order 5. The more you put, the higher n you choose, the more poles you'll have, therefore a higher order transfer function. Its implementation will be more complicated, of course, right? You'll have a lot of RNC circuits and so on, right? Yes? You looked, when you played with these Werkstatt modules, there was a circuit diagram that Alex showed you. That was a low-pass filter. It's like a ladder of RC circuits, right? That was basically a low-pass filter. So it is implementing some kind of low-pass filter. It's not. It may even be this one. I'm not sure. There used to be courses in the old days that showed you what are these filters, Chebyshev, or this one, Butterworth, and what are their transfer functions, and how do you implement them with RC circuits, etc. They don't exist anymore because they are mostly done digitally now. All right, so the rest of this is in the notes. So with that, I'm going to tell you a little more about what we do with transfer functions. I have 14 minutes. I will use it. All right, so one other thing we can do with at least small order transfer functions where there are few poles and zeros is to look at the pole zero locations and predict the frequency response. Right? That's pretty cool. How can I just look at the pole zero picture and say, oh, this is, of course, a low-pass filter, or this is a high-pass filter? How can I do that? Response from poles and zeros. Again, this is going to work for simple systems with only a couple of them. So let's start simple. Let's think of an example where h of s is 1 over s plus 1. Is that low pass, high pass? You should be able to see this anyway, right? The frequency response is h of j omega equals 1 plus j omega. So if you look at the norm, the absolute value rather, of h of j omega, it's 1 over 1 plus omega square root. All right, so it is a low pass. It's a bell-shaped thing. Not too different, in fact. That's actually a Butterworth filter of order 1, right? Because if you go back to this, n equal to 1 means you have only one pole. And that's going to be negative and real at negative omega c, right? So that's the simplest, cheapest low-pass filter you can design. But looking at the poles, how can I tell this is a low-pass filter? So one way to do that is to make a pole zero plot in the complex plane. This is the imaginary axis. This is the real axis. And the pole is at negative 1. Right? So h of j omega, the norm, the absolute value of the magnitude of h of j omega is 1 over j omega plus 1, or 1 plus j omega, absolute value, right? But how can I interpret j omega plus 1 as a vector in the complex plane? J omega plus 1 is j omega minus 1, which is this, right? So if I put a vector starting at negative 1, pointing to j omega, that's j omega plus 1. You guys agree with this? Because that's j omega minus 1, which is plus 1. Yes? So the magnitude of this vector is the magnitude of j omega plus 1. And h of j omega is 1 over that. Okay? So if I trace omega, if I just walk on this imaginary axis, okay, walk this way, increase your omega, and measure your distance to the pole at negative 1. What's going to happen as omega goes to infinity? If omega is going to infinity, if I'm walking up the imaginary axis, I'm getting farther and farther and farther away from negative 1. So it's going to infinity. Therefore, the frequency response 1 over that is going to 0, right? So what about it? What happens as I come closer here if I walk this way? It's getting shorter, right? Is that clear? So if I start at omega, what's my distance? Initially it's 1. So I start at a distance of 1. When I'm here, I'm 1 units away. And as I go up, I'm getting farther and farther and farther. And as omega goes to infinity, I'm going converging to 0. So that's why we get this type of frequency response. So that's a geometric interpretation based on where the poles and, well, in this case there are no zeros, where the poles are, right? So same argument can be applied to this the Butterworth filter, right? If I'm walking here, start at omega equal to 0, then my frequency response is 1 over these distances multiplied. And see how they are nicely spread out? So if I'm going farther away from one, I'm getting closer to another. So they kind of nicely balance each other out. So as long as I'm in this region between 0 and omega c, you know, the distance is sort of leveling out. I mean, overall it's declining a little bit, but it's keeping it pretty constant, right? But then the moment I go beyond omega c, then I'm getting farther and farther away from all the poles. So that means I will quickly decay to 0. And that basically is why we have this nice and smooth convergence of the Butterworth response, right? So let's look at another example. I think you get the idea, but just one more example will not kill us. You could, for example, now include a 0. You could say, what if h of s is s plus 1 by s plus 10? Well, that means the pole is at negative 1, no, negative 10 rather, and the 0 is at negative 1. H of j omega is 1 plus j omega by 10 plus j omega. So the norm of h of j omega is the norm. Why do I keep saying norm? Absolute value of j omega. I guess in 1D it's also the norm, but yeah. 10 plus j omega, right? So that means we are looking at the ratio of two distances. The distance to 1, when I'm sitting at omega, divided by the distance to 10. What is that ratio when I'm at omega equal to 0? One over 10. As omega is going to infinity, they are both really far away. It's like plane taking off, you know, two houses, you're equidistant from them. So eventually it will converge to 1. Okay, so it's going to look like this. Okay, have you seen Bode plots in 16? That's basically it. I mean, that's the main idea behind Bode plots. You can also talk about what happens to the phase of these things. This formula applies to the magnitudes. For phase, what can you tell me about the phase of AH of j omega? If you are dividing two complex numbers, the phase of the division is the phase of the top minus phase of the bottom. So 1 plus j omega, 1 plus 10, 10 plus j omega, right? So what is the angle of 1 plus j omega? It's this angle. And the angle of 10 plus j omega is this. If you remember your high school geometry, the difference between those two angles is really this angle. Okay? So then you're asking yourself, as I stare at omega, at which point the angle is 0, right? Because they are both aligned, right? There's no angle between them and omega is 0. Starting at 0, how is that going to change as I walk up the imaginary axis? Goes to where in the end? Eventually it becomes 0 again. So it starts at 0, ends at 0, but in the meantime, it has a little bump, right? It's going to look something like this. Okay? So Bode plots are basically straight line approximations to these things, also using logarithmic scales for both the omega and the magnitude. If we have time, if there are no further outages, we may get into that a little bit, but we'll see. All right. So, finally, I want to tell you about second-order systems. So the canonical representation for a second-order system is this. I told you before, I'm going to have a second-order polynomial in the denominator. I could parameterize this polynomial by its coefficients, right? S squared plus a number plus another number. But the poles of the second-order polynomial will not depend in a pretty way on these two coefficients. A better parameterization that gives us where exactly the poles are is the following. That looks weird at first sight, but you have to get used to it. 2 times zeta is a parameter, omega n is another parameter, times s plus omega n squared. Okay, so that's what we use for the denominator. Instead of like a1, a0, we use these. The reason is that the roots are then easy to find. The roots are, the poles of this are at s by omega n, if I scale everything by omega n, negative zeta plus minus zeta squared minus 1. Okay? Why is that good? Because what is the magnitude of this? So say this is imaginary, okay, zeta is less than 1, right? If I square the real part and square the imaginary part, add them up, what do I get? Zeta squared. So, okay, let me write this. Okay, zeta is smaller than 1. Okay, so let me be a little more clear. If zeta is smaller than 1, then I have negative zeta plus minus j times 1 minus zeta squared. Is that better? Okay. Now tell me the magnitude of this. Zeta squared plus 1 minus zeta squared, which is 1. Right? So these are complex conjugate poles on a circle of radius 1. But then we have division by omega n, so that means the poles are again on a half circle with radius omega n. Okay? Zeta basically tells you the real part. Negative zeta is the real part. And then 1 minus zeta squared is the imaginary part. So I have two complex conjugate poles. Okay? So why is this parameterization useful? Because it tells me, the omega n parameter tells me how far away those poles are from the origin. Right? And zeta tells me how, how close to being real they are, right? So zeta is the real part. As zeta comes close to 1, that means these poles have moved closer to here, right? As zeta comes close to 0, it means they are close to here, okay? In fact, you can define this angle here to be theta. Then what that means is that tangent of theta is, cosine, what is cosine of theta? This is zeta, right? This is 1. If omega n is equal to 1, that's 1, right? So cosine theta is zeta, right? So that means you have two poles that make an angle of theta with the real axis, and their distance from the origin is omega n. That's why this parameterization is useful. So what do you think the frequency response will look like? You start here, walk here, and measure your distance to the two poles, divide 1 by the product of those, right? Where will you go eventually? Just based on our geometric interpretation, you will start constant or, decay to 0 eventually, because when you're far away, both poles are really far away, right? Right? Does that make sense? There is something that's not completely accurate about this picture, which happens when this theta is really large, bigger than 45 degrees. What happens when theta exceeds 45 degrees is around the frequency omega n, we start having a peak. Okay? When theta is bigger than 45 degrees. So that's the case where the damping is pretty bad. So the poles are closer to the imaginary axis than they are to the real axis, right? And that's when you can show that this h will give you a frequency response that jumps and then goes back. It's no longer monotonically decreasing. What do we call this bump? Resonance, because if you apply its input, sinusoidal input, with a frequency in this range, the system will amplify that. All right?